Hi, it's Mrs. Geiger here. So you should have already watched Naming Compounds Part 1, so we're going to do Naming Compounds Part 2. I wanted to break it up so that it wasn't too long of a video. All right, so we're going to talk about something called the stock system. We're still talking about ionic bonding here. So we are still talking about how to name ionic compounds. All right, so the stock system. So if a metal can become stable in different ways, they will have more than one oxidation state listed. So when you look at the Regents version of the reference table, you'll see that some metals have more than one oxidation state. You need to identify which type of ion is in the compound. And we do that using Roman numerals. All right, so Roman numerals, you should know, use capital I's. So 1 is just one capital I. 2 is 2. And sometimes we write it like this, where we kind of connect the I's to each other. 3 is 3 Roman numerals. 4 is I and then a V. And sometimes we put actually the top and the bottom there for the V. 5 is just a V. 6 is V and then an I. 7 is VII. Cross them all. 8 is VIII. 9. We can't go up to 9. 8 is actually the highest, and that's because of the number of valence electrons. But you should basically know that I is 1, V is 5. Do you know what 10 is? Very cool. 10 is X. Wonderful. So Roman numerals, you might have seen this in other classes, very often chapters, in a textbook, or if you are a football fan, the Super Bowl, they do in Roman numerals. Now, why Roman numerals? Well, we already have our regular numbers, or Arabic numbers, for subscripts and charges and coefficients. So we need to be able to distinguish what the charge is here. So they IUPAC decided that they were going to use Roman numerals to talk about the charge. So if we have an example here of copper 1 chloride, and we'll do copper 2 chloride, those are the two ways in which copper can form ions. That one tells you the oxidation number or the charge on that ion. So this would be a copper. Copper has the symbol of Cu. And the 1 means that it has a 1 plus charge. Now, what would the charge on a chloride ion be? So find chlorine on the periodic table. How many valence electrons does chlorine have? That's right, it has 7. So when chlorine forms an ion, a chloride ion, it's going to form an ion by gaining 1 electron. All right, it has 6, so it's going to form an ion by gaining 1 electron. So what would the charge be on that chloride ion? You're right, it would be 1 minus. So we're going to have Cl 1 minus. So chloride always has a 1 minus charge. We know that because of the number of valence electrons and the octet rule. So you're going to say to yourself, do the charges add up to 0? In this case, they do. And that tells us that there is no need to multiply either the copper or the chloride because they're already adding up to 0. So we don't need multiples. So that tells us that we're going to have Cu, Cl, a 1-to-1 ratio of copper to chloride. And our formula for copper 1 chloride is CuCl. Let's do another example. Our next example is going to be copper 2 chloride. sorry. All right, so copper 2 chloride. I don't know why this keeps happening. Oh, I keep resting my hand on the touchpad, that's why. All right, so copper 2, still copper, still an ion, but now instead of a +1 charge, this is going to have a 2+ charge. Chloride is still the same. It's going to have a 1- charge. So in this example, we can draw out a Lewis dot diagram, or we can just see that the lowest common multiple is going to be 2. So if copper loses 2 electrons and chloride gains 1 electron, we can't use a 1-to-1 ratio. Instead, we're going to need 2 of these Cl minus 1 minus in order to balance out the charge. Because remember, when we say balance out the charge, we mean everything adds up to 0. So the formula for copper 2 chloride would be CuCl2, where we need to have 2 chloride ions for every 1 copper. All right, now let's do another example. Our next example is going to be iron 3 oxide versus iron 2 oxide. So go ahead and pause the video and see if you can figure out how many irons, how many oxygens you're going to have in each of these examples. All right, now that we're back after you unpause the video, let's take a look. So iron has the symbol of Fe. This 3 in Roman numerals tells us that the iron is going to have a 3+ charge. Oxide is oxygen. And what's the charge going to be on this oxide ion? Well, oxygen has 1, 2, 3, 4, 5, 6 valence electrons. So that means that when oxide is formed, it's always going to have a 2- charge. So now that you know that iron is going to have a 3+ charge and oxide is going to have a 2- charge, how many irons do you need? And how many oxygens do you need to balance out the charge, since these do not add up to 0? So you're going to say to yourself, okay, it's 3 and 2. What's the lowest common multiple between 3 and 2? That's right, it's 6. So we're going to need to multiply iron in order to get to +6. So how many iron 3+ are we going to need? That's right, we're going to need 2. So I'm going to draw another iron +3. Oh, sorry, I lost my... Adios, my bad. Try this again. Fe 3+. So that gives me a total charge of +6 for all of my irons. Now, how many oxides are we going to need to get to -6, right? Because we want it all to always add up to 0. And I'll draw a little cross through that so that you know that that's a 0, not an O. It's a little confusing sometimes. That's right, you're going to need 3 of these. So I'm going to have... I'll color code this correctly. You're going to need 3 of these. So that means that the formula for iron 3 oxide is Fe2O3. I'm going to need 3 oxides with a charge of 2- to balance out the charge of those 2 irons with the 3+ charge. Now there's a little trick here. You might see a pattern. We have Fe3+ and we have O2-. And the formula is Fe2O3. So the trick is called crisscrossing. Crisscrossing is just a way to get to the lowest common multiple faster. You only need to do this, you only need to multiply when the charges don't already add up to 0. So, if you take the absolute value of the charge of the cation, that's going to be the subscript for the anion. And if you take the absolute value of the charge of the anion, that's going to be the subscript for the cation. And the reason that works is because of the lowest common multiple. And if I scroll up, you'll notice that here in copper 1 chloride, we didn't need to multiply. So they're in a 1-to-1 ratio. But do you see how that trick actually works in copper 2 chloride? Because the charge on the cation ends up being the subscript on the anion. Now, when there's a 1, we don't write anything here. There's 1 copper, so there's no need to write the subscript there. It's just not, you don't need to multiply it. All right, let's try another example. Our next example is going to be iron 2 oxide. So go ahead and pause the video and see if you can figure out what the ions are and what the charges are on iron 2 oxide. All right, wonderful. Now that we're back, iron has the symbol of Fe. 2 means that it has a 2+ charge. Oxide is going to always be 2-. So you say to yourself, do the charges add up to 0? Or do I need to multiply? You got it. The charges add up to 0, so there's no need to multiply. So these are going to be in a 1-to-1 ratio, and the formula here is going to just be FeO, the most ugly compound ever. That's a Spanish speaker joke. Feo is ugly, and that's actually rust, iron 2 oxide, so it kind of is ugly, and that's why I think that that joke is funny. All right, so these are in a 1-to-1 ratio because the charges add up to 0, while iron 3 oxide is in a 2-to-3 ratio because you need to multiply. So that's why this is really important. It's really important that you pay attention to the charges. All right, our next example is going to be backwards. We're going to write the name out for this ion, and we're going to figure out what the charge is on the metal here. So, COCl3, what would the name of this compound be? So, CO is the symbol for cobalt, you're right. And we know that cobalt can form more than one ion. So I'm going to leave space here for my Roman numerals in parentheses. And what would Cl be? What ion is that? You're right, it's chloride. All right, so we have to figure out what the charge is on cobalt here. I'm going to do this using a... All right, wonderful. So I'm going to do this by drawing a Lewis dot diagram to figure this out. So I'm going to have my cobalt, right? And then I need to figure out what the charge is going to be on my chloride ion. So chloride has 7 valence electrons. So it's always going to react by gaining the 1, which means it's going to have a -1 charge. So if I know that my cobalt and my chloride have to add up to 0, and I know that I'm going to end up with 3 of these -1 chlorides, how many electrons total were lost by the cobalt? You guys got it. There's going to be 3 total electrons that are lost, and I wrote those in blue. So that means that my cobalt is going to have a 3+ charge. And how do you write a 3 in Roman numerals? That's right, it's going to be I. So this is going to be called cobalt 3 chloride. And remember, I showed you there's a little trick, right? The trick here is whatever the subscript is on the anion, it's going to end up being the charge on the cation. All right, so cobalt 3 chloride is written as COCl3. Down below here, I'm just going to show you, you should just write these down, some common elements that have multiple oxidation states. So iron can be 2+ or 3+. Copper can be 1+ or 2+. Oh, there's the bell. Thank you. So you guys can just copy these down: nickel, chromium, cobalt, and gold. Those are all common transition elements that have more than one oxidation state. Additionally, there are common transition elements that only have one oxidation state, but you might think they would have more than one. Zinc is always 2+, and silver is always 1+. And so you don't need Roman numerals for those ones because zinc is always going to be 2+, so we don't write zinc 2 oxide. We just say zinc oxide. Same thing with silver. All right. Thank you.